In F1, we met the parabola y squared equals 4ax. And we came across the focus, which was at a0, and the directrix, which was the line x equals minus a. And every point on the parabola, the distance from the focus, SP, was the same as the distance from the directrix, Pn. When this happens, we say that the eccentricity, E, is 1. More about that later. But let's see what happens if we move P around a little bit. If we keep those two distances equal, Bs equals Pn, you can see that the point P is tracing out a nice, happy-looking parabola. Well, let's put a trace on that so that we can actually see where it's going. And now, if I move P around, you'll see that we have the shape that we're used to. There is a parabola. This is y squared equals 4ax. The important thing here is that SP is 1 times Pn, and this gives us an eccentricity, E is 1. But what happens if we vary E? First of all, let's look at what happens if we take E is less than 1. In this, I've taken E is 0.8. And so the length from P to S, the distance SP, is now 0.8 times Pn. But if you can look at that, that looks quite reasonable. What happens if I move P around now? If I can get P to move, yes, there it goes. Oh, I don't want to move the point. As I move around, we can see that the length of PS is still around about 0.8 times Pn. Keep moving P, and this is set up so that that ratio stays the same the whole time. Well, I think you can see what we're looking at now. We're looking at something which looks as though it might be an ellipse. Let's put a trace on that and have a look at it. I'm moving P again. There it goes. And we have an ellipse. Well, there's a lot of symmetry in an ellipse. This ellipse we've drawn by thinking of the distance of P from 4, 0 is E, which is 0.8 times the distance from the directrix. Well, with all this symmetry around, we should have an equivalent point over here at minus 4 and an equivalent line at minus 6.25. And an ellipse actually has 2 foci and 2 directrices. Let's have a look at that. Here we can see the same ellipse, focus at 4, directrix at 6.25. But now I have a focus at minus 4, directrix of minus 6.25. And here, if I move this point Q, you can see that QS dashed all the time, QS dashed is approximately equal to, well, it's exactly equal to, but we're just looking at roughly 0.8 times QM. And so if I can draw my ellipse using P with 4 and 6.25, I could also draw my ellipse using Q and minus 4 and minus 6.25. If we now generalize that result, we can start off with a fixed point S, which is going to be the focus, and that I'm going to take at AE0, and a vertical line, the directrix, which I'm taking at x equals A over E. And I'm going to look at what happens to this point P as it varies, subject to the condition that SP is E times Pn, where E is smaller than 1. So SP is E times Pn. What can we say about X and Y? Well, if we take SP equals Pn and square it, we will get that SP squared is E squared Pn squared. SP squared, distance between 2 points. We get the x coordinates, x minus ae squared. We get the y coordinates, y minus 0 squared is e squared Pn squared. Well, the x coordinate at n is a over e. The x coordinate at p is x. So the length of Pn is a over e minus x, and we want Pn squared. Little bit of algebra now. X squared minus 2aex plus a squared e squared plus y squared. Can we multiply out and square, multiply by e squared at the same time? A squared over e squared times e squared minus 2a over e times e squared x plus e squared x squared. Well, we have minus 2aex on each side. That disappears. Subtracting x squared e squared from each side. Keep the y squared and subtract a squared e squared. Divide both sides by the right-hand side and factorize at the same time. X squared 1 minus e squared divided by a squared 1 minus e squared plus y squared over a squared 1 minus e squared is 1. Well, we can cancel the 1 minus e squared. And we are left with an equation like that. The important thing is that 1 minus e squared is actually greater than 0. It's a positive number because e is less than 1. I wouldn't get that equation otherwise. Because that's true, because it's positive, I can write b squared equal to a squared 1 minus e squared, and that gives me the standard equation of an ellipse. And so we've shown that this condition here, SP is EPN, where E is less than 1, will mean that P moves in a circle. And here is a picture showing P on the ellipse with the previous lengths and points. So here we have the ellipse x squared over a squared plus y squared over b squared is 1. And the result that we picked up from this is that the connection between A, B, and E is that b squared is equal to a squared 1 minus e squared. Well, let's have a look at an example. How can we find, from the standard equation of the ellipse, where the focuses or the foci and directrices are? Well, we are starting from x squared over a squared plus y squared over b squared. And what I've just said is that b squared is a squared 1 minus e squared. In this case, b is 4. So you've got 4 squared is a is 5, 5 squared 1 minus e squared, which gives you 16 over 25 is 1 minus e squared. And that gives you that e squared is 9/25, and so E is 3/5. E, the eccentricity, is the ratio of lengths, and so E must always be a positive number. If that's the case, then we now have A is 5, E is 3/5, and therefore the foci are at plus or minus AE0. In other words, plus or minus 3/5 times 5 is 3, 0. And the directrices are x equals plus or minus A over E, and that in this case is going to be A is 5 divided by 3/5, that is 25/3. So we have foci and the directrices quite easily. You must remember this little result. B squared is A squared 1 minus E squared. And since E is less than 1, this equation will work. I'm now going to look at a little result which will allow us to draw an ellipse with a piece of string. Let's suppose that we have an ellipse with eccentricity E. Then my two directrices will be x equals A over E and x equals minus A over E. SP will be E times Pn. And if we use the alternative focus idea, S dashed P will be equal to E times Pn dashed. This relies on the fact that the ellipse has two foci and two directrices. So let's just write that down. We have just said that SP is equal to E times Pn, using S as a focus. And if we look at the other focus, S dashed P is going to be E times Pn dashed. And if I add that together, I get SP plus S dashed P is going to be equal to E, let's factorize while we're doing it, Pn plus Pn dashed. Well, Pn plus Pn dashed is just the total distance from n to n dashed. A over E that way, A over E that way, the total distance is 2A over E. So that's E times 2A over E, which tells us that SP plus S dashed P is 2A. The important thing is that this is constant. And this is the result that we're going to use to draw an ellipse with a piece of string. In this video, I'm using the 3 green lines to represent a loop of string. The string passes round 2 fixed points, S and S dashed, and we tighten it by pulling it up to the point P. The distance between S and S dashed is fixed. The length of the piece of string doesn't change, and so the total distance of PS plus PS dashed will be constant. This is the result that we've just proved if P lies on an ellipse. I'm now going to use that result the other way round to draw an ellipse. If I move P so that the total distance PS plus PS dashed remains constant, in other words, this is simulating a piece of string. If I was in the classroom, I would actually have a piece of string and you would see this happening. And you can see that this seems to be moving in a pretty good ellipse. Well, let's have a closer look at what's going on there. If we put the trace on, then we can actually see the path that P is taking. There it goes. Yes, and we get a pretty good ellipse. So that is how you can draw an ellipse using a piece of string.